And we, in fact, owe our entire existence to this scaffolding that's set up of dark matter in the early universe.
What happens is that first the dark matter forms the structure. The ordinary matter then follows the dark matter. The ordinary matter is hydrogen and helium at this stage. And the hydrogen and helium fall to the center of the dark matter halos that are forming.
We're taking the Earth inside the Dark Age. A time over 12.5 billion years ago. The sight is spectacular. Our skies are lit by the first stars. They're like Tia's the hydrogen fog, bathing the Earth in strong ultraviolet energy. These first stars will change the way we see the universe forever. Tom Abel studies the life and death of these early stars.
The beautiful thing is that we now have computers. We program them with the laws of physics. Put in some gravity, hydrodynamics, how gases move around, some of the chemistry. And as we evolve it all together, we gain an intuition of how stars come about. And in the case of the very first stars, this is absolutely crucial.
Abel begins with the basic ingredients available during the Dark Ages: hydrogen, helium, dark matter, and gravity. Using computer models, Abel recreates the lives of these early stars.
Here we see one of the first stars in the universe. It's 100 times as massive as the sun, 1,000,000 times as bright.
The first stars are huge, swollen by the massive amounts of hydrogen gas pulled in by the gravitational force of dark matter.
And so even though they have all this fuel to burn, you'd think they could live for a long time. They run through it so quickly that even after a few million years, they're already dead.
The first stars are fierce, high-octane stars, burning their hydrogen fuel at tremendous rates, racing through their life cycle.
They like the rock stars. They live fast and die young. They run through that fuel very quickly, and even after just a few million years, they already die.
They die in some of the most violent explosions ever to rock the universe. Gigantic supernovas that shine brilliantly. The energy given off during the life and death of these massive stars leads to a miraculous transformation.
From these stars likely came the first generation of black holes. Cosmologist Tiziana Di Matteo is part of a wider effort to see what marked these early black holes left on the universe. Her computer program simulates the action of gravity on gas, the formation of stars, galaxies, and black holes. Her goal is to create a virtual universe that evolves like the real one did, with black holes and galaxies emerging and growing together. Our Milky Way galaxy is located in a quiet part of the universe, with relatively few other galaxies around it. Move out across the cosmic void, 50 million light-years away, and you encounter the Great Virgo Cluster, filled with thousands of galaxies. Recent telescope surveys show that this region is part of a larger pattern of galaxies resembling a vast spider's web. To get her virtual universe to look like this, Tiziana needs to know what cosmic conditions gave rise to black holes and galaxies in the first place.
So it's a beautiful problem because we start from extremely well-specified initial conditions. We know the initial condition of the universe, and that's very rare in astrophysics, in cosmology, in any branch of physics.
Details of what the universe was like in its earliest times have come courtesy of a breakthrough observatory called WMAP. It found a blotchy pattern in a kind of radiation generated soon after the Big Bang. Astronomers believe this pattern is the origin of the spider's web structure they see in their telescopes. It defines the beginning point of Tiziana's simulation. She sets her virtual universe in motion. It covers a region in the shape of a cube over 100 million light years on a side. The result, an intricate cosmic web with gravity drawing matter into filaments and knots on the largest of scales. In places where filaments come together, galaxies and black holes first begin to appear.
All the matter that is coming in from the large scale will also allow the black hole to grow because of these gases being transported from large scale all the way into the galaxy, and the galaxy all the way into the center, and therefore feeding and growing these central black holes at a very high rate.
In this sequence drawn from her simulation, the circles indicate the appearance of black holes within the data. What she finds is that as these black holes gain mass, gravity pulls them toward the densest regions, where a few grow larger than all the rest. How did these chosen few black holes grow so rapidly? The orbiting Chandra X-ray Observatory recently turned up evidence at the centers of galaxies back in the time of the early universe. These images show its remarkable find, actual supermassive black hole pairs, beginning what astronomers believe is a dance of death. In most cases, their forward momentum simply causes them to go into orbit around each other, like a planet around a sun. This orbit can go on for billions of years. To grow large, one black hole must draw the other in, close enough to swallow it. This simulation shows what happens. As two black holes get close, they turn space into a turbulent sea of gravity waves. These waves have the effect of carrying energy away from the orbit itself. That allows the pair to draw each other in and merge into one.
We go back to half of the age of the universe, and all of these black holes are swallowing large amounts of gas. So it's a fun time. It's sort of the golden age for the growth of most black holes.
At the same time, a black hole jet can seed the surrounding regions with the heavy elements needed to form solar systems and planets like ours.
The black hole also has the property that as it spins on its axis, as the Earth spins, it drags space into a whirling motion like the air in a tornado, faster near the horizon, slower farther away, just as the air in a tornado is whirling faster near the core than it is farther away.
In the eye of this cosmic tornado, gas and stars flow into the hole along a rapidly spinning disk. The spinning motion generates magnetic fields that twist around as matter swirls in. These fields channel some of the inflowing matter out into a pair of high-energy jets.
So we can extract then the rotational energy of a black hole. Nature can extract it. And the amount of energy you can get out is enormously larger than all the energy you can get from burning all the nuclear fuel inside of stars.
It's the equations of Albert Einstein that describe the source of this incredible power. the extreme warping of space just outside the black hole. What we can learn from these equations doesn't stop at the event horizon. They can also let us enter, with our minds, the realm within a black hole.
80 seconds. Rangers go.
45 seconds.
Mounted in the nose of a rocket just up the beach is the next generation cosmic explorer.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, go.
0. Liftoff. Delta rocket carrying in blast. Gamma ray telescope.
The Fermi Gamma Ray Space Telescope is part of a larger effort to explore the role black holes play in shaping the universe.
Farewell. That's on the other side. Yeah. To me, the idea that we're standing here on this planet in our own little area of our galaxy, we're able to look around and make meaningful measurements, have a theoretical understanding of the entire universe in which we live, to me is something that all of humankind can justifiably take pride in.
On Earth, cities are built with iron girders and concrete beams. An invisible scaffold which holds buildings up against the pull of gravity. Without this scaffolding, skyscrapers would crumble and bridges collapse. Gravity governs Earth and the entire universe. Anything that has mass has a gravitational pull. The more the mass, the stronger the pull. With 200 billion stars, the Milky Way has a huge mass and a tremendous gravitational attraction to match. So, like a building, our galaxy also needs propping up against the force of gravity.
Imagine the disk of our galaxy. If you just took a disk of stars and put it there, gravity would tend to make this disk collapse in on itself, and it would immediately just fall together. That's not what we see with the galaxy. What's actually going on is the stars are orbiting around the center, and that's what keeps them from falling in much the same way that the Earth is orbiting around the sun.
The planets in our solar system are in a delicate balance. Gravity pulls them towards the sun, while their orbital velocity wants to fling them out into space. In order to stay balanced, planets further from the sun must orbit more slowly.
If you go to more distant planets at the edge of the solar system, they're going around the sun much more slowly than the Earth is, and that's because the gravity is weaker there.
The same should hold true for stars in the Milky Way. They all orbit the center of the galaxy. But the stars in the outer arm should be traveling more slowly than those closer to the galaxy's heart.
What's interesting is that's not what's going on. The stars in the outer parts of the galaxy are spinning around just as quickly as those in the inner parts.
And they're not the only ones.
It's not just our galaxy, it's every galaxy we look at. Every galaxy we look at seems to be spinning too fast in its outer parts.
These speeding stars should be flung out of the galaxy altogether, but they're not.
That is a puzzle. This means that there's a lot more mass there that we just can't see.
Mass that produces the gravity that holds these stars in their orbits. But when astronomers look for the mass, there appears to be nothing there. Leading cosmologists like Joel Primack to an astounding conclusion.
All of the galaxies, all of the stars and gas and dust and planets and everything else that we can see with our greatest telescopes represent about 0.5% of what's actually out there. The rest is invisible. It's mostly some mysterious substance that we call dark matter.
You can't see dark matter. The reason why you can see normal matter is because light shines on it and reflects off of it. That's how you can see me. Dark matter doesn't work that way. The light goes right through the dark matter. The way we detect dark matter is because it has mass. Anything with mass affects other things via gravity. That's the golden rule of mass. That's what mass does. It tugs on other things because of gravity.
Without dark matter, the Milky Way couldn't exist.
So the galaxy is spinning. The galaxy is spinning fairly rapidly. The reason why it can spin so rapidly is because it has so much dark matter. The dark matter has a lot of mass, and therefore it has a lot of gravity, and that's what keeps the stars whizzing around. If you were to magically take all of the dark matter away from our galaxy, it would fly apart. The stars would just keep going straight, and in a very short amount of time, the galaxy would just be gone.
There'd be just a mess of stuff flying every which way. And that's not just true of our galaxy, it's true of every galaxy and every cluster of galaxies in the universe. They're all held together by this invisible stuff that we call dark matter.
So we need the dark matter. It's the glue that holds galaxies together.
The discovery of dark matter has revolutionized our picture of the Milky Way. The stars of the galaxy represent just a fraction of its mass. The rest is made up of an invisible halo of dark matter, surrounding every single star and every creature in the galaxy.
The stars are just the central region. The halo is at least 10 times bigger and weighs much more than 10 times more than all the stars and gas and dust that we can see. It's that whole structure that's the real Milky Way galaxy. And that's not just true of our galaxy, it's true of every galaxy we've ever studied.
But dark matter does more than simply hold galaxies together. Astronomers now think it binds the Milky Way into an extraordinary structure with billions of other galaxies. A structure that reaches to the very edge of the universe. We've left our home galaxy to take the Earth across billions of light years of space and time.
One of the great things about telescopes is they're time machines. Because light travels at a finite speed, when we look at distant objects, we see them as they were when the light left them.
As astronomers look back over billions of years, they see a universe teeming with galaxies. But these galaxies aren't scattered randomly through space. They cluster along delicate filaments woven in an intricate structure. A vast cosmic web that holds the answer to the birth of galaxies themselves.
Here we are at NASA Ames, the research center where we have the Pleiades supercomputer. Each one of these cabinets contains 512 processors. Let me show you. So that's half a terabyte in each one of these cabinets. There's 110 of these cabinets to make up the entire Pleiades supercomputer. So this is a really big supercomputer. This is NASA's biggest.
The challenge is equally big, to develop a virtual universe from its early beginnings all the way to the present day, to see what role dark matter might have played in shaping the cosmos. If you tried to do this on a home computer, it would take over 680 years.
If we're doing our job right, we can put the pictures into a video, if you like, that shows the whole structure of the universe.
And this is the end result. It's called Bolshoi, an amazing visualization of what the structure of dark matter might look like in the universe today.
So what we're looking at is a region about 200 million light years across, which is actually just a small part of our really big simulation that we call Bolshoi, which is Russian for big. Everything that you see here is actually completely invisible. It's not the visible universe that you're seeing. The bright spots are dark matter. They're the halos of dark matter within which galaxies form. And each one of these little blobs would represent probably one or at most a couple of Milky Way-sized galaxies. And you can see that the galaxies are in long chains, filaments we call them. Basically, all the structure is forming along these filaments of dark matter.
Now comes the real test of success. Premack compares the Bolshoi predictions with the actual structure of galaxies scientists see in the universe.
As far as we can tell, these simulated universes that we make in the supercomputers look just like the observed universe. There don't seem to be any discrepancies at all. This is exactly the way we see the galaxies distributed in the observed universe.
The Bolshoi simulations are astounding. They match the pattern of galaxies seen in the cosmos today perfectly. It's persuasive evidence that dark matter has been sculpting the universe for billions of years.
As important as it is to our very existence, astronomers so far have no idea what dark matter is. This table shows us every element in the universe that we commonly experience on a daily basis. All of the physical matter that we can see, touch, taste, or feel is on this table, but not dark matter. Thanks to Hubble, astronomers found a way to locate and measure it. What they found is that there is 5 times more dark matter in the universe than physical matter. But even if we add all the dark matter to all the physical matter that forms stars and planets and people, it turns out that we are still missing about 2/3 of the universe. So, what is the rest of the universe made of? Once again, scientists turn to Hubble for answers.
In a fraction of a second, the universe underwent a violent expansion, sending space hurtling outward. Space has been expanding ever since. For decades, most scientists thought that expansion must be slowing down thanks to the pull of gravity.
When I toss an apple up, the gravity of the Earth eventually stops it and brings it back. And just like the apple slows down with time, so too the universe should have been slowing down in its expansion because of the gravitational attraction of all matter and energy for all other matter and energy.
But that raised the question, what is the ultimate fate of the cosmos? Would space go on expanding forever? Or would gravity eventually stop space from expanding, causing it to collapse back on itself in a big crunch? To solve this mystery, two teams of astronomers set out to measure the slowing of the expansion using a novel tool: exploding stars called supernovas.
So a supernova is a star that ends its life in a massive explosion. They're extremely luminous. They can be as bright as 1 billion suns.
What makes supernova great is that they're very similar when they explode. They all get about the same brightness and then they fade away in just about the same way.
Because the explosions are so bright and uniform, the teams reasoned that these supernovas would act as very precise cosmic beacons, allowing them to track how the expansion of space has slowed over time. The trouble is, supernovas are extremely rare. To find enough of them, Perlmutter spent years calling astronomers around the globe, begging for time on their telescopes.
We needed the biggest telescopes in the world. We needed perfect conditions. And in those perfect conditions, I would be calling people up at the middle of their night when they're trying to do some serious work, and I'd be saying, I know that you have a very busy schedule, but by any chance, if you could just squeeze in this half-hour observation, it would really be very interesting to us.
When they finally had enough data to chart how much the pull of gravity was slowing the expansion of the universe, they were in for a surprise.
The results looked a little bit strange. They didn't really show any slowing of the universe at all. Very surprising. Actually, a universe that's actually speeding up.
It was as though space, which we really thought was nothing, actually had an inherent springiness to it. And so space did not want to be compressed. Space actually wants to push the universe apart.
It looked like the universe was expanding faster and faster with time, accelerating rather than decelerating.
My immediate response was, I have to figure out why this is wrong. This can't be right.
But it was right, and most scientists converged on one explanation. There's something that fills space and counteracts the pull of ordinary attractive gravity, pushing galaxies apart and stretching the very fabric of the cosmos. This mysterious substance filling space has been dubbed dark energy, and it's turned our picture of the universe upside down.
Over the largest distances, dark energy dominates the contents of the universe, and we don't know what it is.
If you do sort of a survey, a census of all the energy in the universe, dark energy turns out to be about 70% of the universe. And up until a decade ago, nobody imagined such stuff even existed.
So in essence, the weight of empty space itself is 70% of the weight of the entire universe. That's roughly the same percentage of Earth's surface that's covered by water. Imagine we didn't know what water is. That's where we stand with dark energy.
We're really clueless about how to explain it. We have all of this fancy scientific apparatus of quantum mechanics and relativity and particle physics that we've developed in the last 100 years, and none of that works to explain dark energy.
Hubble's results convinces astronomers that they must think of the universe in an entirely new way. The only explanation is as simple as it is unlikely. Something is causing the expansion of the universe to accelerate. An unseen force called dark energy.
Dark energy is another manifestation of a familiar force. So gravity is a familiar force, but we've never seen it act this way before.
But the darkest part of this mysterious force is its future. Over time, it will grow in strength. This means that one day, dark energy will become stronger than gravity, stronger than even the forces which bind atoms together.
Every bound thing becomes unbound, including eventually at the most subatomic level.
Our universe, it seems, is living on borrowed time. The universe will one day end in a cosmic apocalypse that scientists call the Big Rip.
Our picture of space has gone through a remarkable transformation. Back in Newton's time, space was just the container. It didn't do anything at all. Then through Einstein, space begins to affect how objects move. Then with Casimir, literally objects can be pushed by the activity even in empty space. And now through the ideas of Higgs and dark energy, the very expansion of the universe may be coming from the energy of empty space itself. I don't think anybody would have thought that space would have this kind of rich and profound impact on the nature of reality. But as far as we've come, the journey that began with Isaac Newton's picture of space as something like a stage is not yet finished. As we examine the fabric of the cosmos ever more closely, we may well find far more surprises than anyone ever imagined. Take me, for example. I seem real enough, don't I? Well, yes. But surprising new clues are emerging that everything, you and I and even space itself, may actually be a kind of hologram. That is, everything we see and experience, everything we call our familiar three-dimensional reality, may be a projection of information that's stored on a thin, distant, two-dimensional surface. Sort of the way the information for this hologram is stored on this thin piece of plastic. Now, holograms are something we're all familiar with, from the security symbol you find on most credit cards. But the universe is a hologram? That's one of the most drastic revisions to our picture of space and reality ever proposed. And the evidence for it comes from some of the strangest realms of space, black holes.
This is a real disconnect, and it's very hard to get your head around. Modern ideas coming from black holes tell us that reality is two-dimensional, that the three-dimensional world, the full-bodied three-dimensional world, is a kind of image of a hologram on the boundary of the region of space. This is a very strange thing. When I was a younger physicist, I would have thought any physicist who said that was absolutely crazy.
Here's a way to think about this. Imagine I took my wallet and threw it into a black hole. What would happen? We used to think that since nothing, not even light, can escape the immense gravity of a black hole, my wallet would be lost forever. But it now seems that may not be the whole story. Recently, scientists exploring the math describing black holes made a curious discovery. Even as my wallet disappears into the black hole, a copy of all the information it contains seems to get smeared out and stored on the surface of the black hole, in much the same way that information is stored in a computer. So, in the end, my wallet exists in two places. There's a three-dimensional version that's lost forever inside the black hole, and a two-dimensional version that remains on the surface as information.
The information content of all the stuff that fell into that black hole can be expressed entirely in terms of just the outside of the black hole. The idea then is that you can capture what's going on inside the black hole by referring only to the outside.
And in theory, I could use the information on the outside of the black hole to reconstruct my wallet. And here's the truly mind-blowing part. Space within a black hole plays by the same rules as space outside a black hole or anywhere else. So if an object inside a black hole can be described by information on the black hole surface, then it might be that everything in the universe, from galaxies and stars to you and me, even space itself, is just a projection of information stored on some distant two-dimensional surface that surrounds us. In other words, what we experience as reality may be something like a hologram.
Is the three-dimensional world an illusion in the same sense that a hologram is an illusion? Perhaps. I'm inclined to think yes, that the three-dimensional world is a kind of illusion, and that the ultimate precise reality is the two-dimensional reality at the surface of the universe.
This idea is so new that physicists are still struggling to understand it. But if it's right, just as Newton and Einstein completely changed our picture of space, we may be on the verge of an even more dramatic revolution. For something that's such a vital part of our everyday lives, space remains kind of like a familiar stranger. It's all around us, but we're still far from having unmasked its true identity. That may take 100 years, it may take 1,000 years, or it may happen tomorrow. But when we solve that mystery, we'll take a giant step toward fully understanding the fabric of the cosmos.
Heaven, West Virginia, Blue Ridge Mountain, Shenandoah River. Life is old there, older than the trees, younger than the mountains, growing like a breeze. Country roads, take me home to the place I belong. Virginia, mountain mama, take me home, country roads. All my memories gather around her, miner's lady, stranger to blue water. Dark and dusty, painted on the sky, misty taste of moonshine, teardrop in my eye. Country roads, take me home to the place